Hello everyone, let's start the session. It's already 6 p.m. So let me introduce myself first. I am Ananya. I am a PhD student in the Department of Electrical Engineering, IIT Bangalore. So welcome to the course Introduction to Semiconductor Devices. So this is week 11. As probably you might have attended few of live sessions that I have conducted. I conduct these live sessions on every Tuesday from 6 to 8. And as always, we will start with a brief discussion of the topics. Those were discussed in the class, and then we'll go to the question and answers. Okay. So this is week 11. We have already discussed about initially a little bit of about quantum mechanics, then concepts of semiconductors and how current flows in semiconductors. Then we discuss different semiconductor devices, how we can control the current in a semiconductor devices like in PN junction or in MOSFET. Okay, so in this week we are discussing optoelectronic devices. Opto means it is related to light, and then electronic is like we are discussing about semiconductor devices in this course. Okay, so as we are discussing optoelectronic devices, so first concept we should know is the optical absorption. Okay, we have discussed about this topics earlier also, so I'll go through it very briefly. You know what is optical absorption already? Absorption. So from where it started, when we first studied about this optical absorption or about photon, when we initially discussed about remaining questions of week 10, so I'll probably take one extra session on Friday. I'm not sure about the timing right now. You will be notified. If not, then I will complete everything in next week, week 12. Okay, so I'm trying to keep this for extra session because otherwise this will also not complete. From where optical absorption comes, we know that we know the wave particle duality of matter. Okay, we know that even though light we consider it like a wave, but actually it has a particle nature also, and the particle quanta of light is known as a photon. Okay, so photon, what is the energy of a photon? Is h nu. Nu is the frequency of the wave, and h is the Planck's constant. We already know the values. Photon is like a massless quantity, so there is no mass associated with it. So we cannot calculate like properties like momentum of photon using this normal mass expression. So we use a slightly different expression for it. That's not important right now. The important point is that light is absorbed in a semiconductor material only when the energy of the photon is higher than the band gap of the semiconductor. Okay, so if h nu is greater than or equal to the band gap of the semiconductor, in that case the photon will be absorbed. The photon will be absorbed, and this photon will create electron and hole pair in the semiconductor. Okay, suppose this is the band gap of the semiconductor, this is EV, conduction valence band H, and this is the conduction band H, and this is EG. When photon that has an energy less than EG, what will happen to that? That photon will transmit through this material. Okay, so for that frequency, for that wavelength, the material will look transparent. Okay, And if the energy of the photon is equal to Eg, so one electron from the valence band edge will go to the conduction band edge. Okay, so one electron and hole pair will be generated for each photon if the h nu is equal to Eg. If h nu is larger than Eg, so maybe a hole from here will go to the conduction band edge. So electron will move to the conduction band, and it will reach to a slightly higher energy than the conduction band edge. So this is the kinetic energy of the electron, and similarly the excess energy, what will be the excess energy, h nu minus Eg, that will be divided between this electron and hole. So electron will get some kinetic energy and hole will also get some kinetic energy. Okay, so the hole will move like deep into the valence band. Okay, and electron will move up in the conduction band. Now how this kinetic energy, how much kinetic energy the electron get and the hole get, that depends on the mass of the electron and hole. So that is also like another part. If you look carefully in the lecture notes, you will see that even in the book also the figure is given. So you will see the electrons, I think the figure is given in the book. Let me check. Yeah, so normally the electrons will have like a slightly higher kinetic energy compared to hole, because electrons are lighter, the mass is less, the kinetic energy is like half mv square, so it is like divided based on the ratio of the mass of electron and hole. Okay, so the how much kinetic energy the electrons achieve and the hole achieve, that depends on the mass. That is the just a point that I want to tell you. This is not important for our today's discussion, but if you are interested, you can check those. Okay, now what happens to the photon? Photon is it get absorbed, and photon gets absorbed, so and that energy of the photon is transferred to the electron and hole pair generation, to that process. Okay, now what we have learned, that suppose we have a block of semiconductor and in n number of photons is incident on the semiconductor, then some of the photons will get absorbed in the semiconductor, so the number of photons actually decreases after say n number of photons are at the edge of the semiconductor initially, that will decrease with a distance. Okay, now how it decrease, that rate, how it changes, dn by dx, if n is the number of photon, is proportional to n. Okay, minus n, because it decreases, this negative sign increases now. Okay, and when we have this kind of expression, we can have a proportionality constant, that is minus alpha n. So number of photons at any point x is initial number of photons, and that decreases exponentially, because we know that when we have like a differential first order differential equation like this, so the solution is like this. So n naught exponential minus alpha x. And what is alpha? Alpha is the absorption coefficient. Okay, now we know that the absorption of photon, it depends on whether the energy of the photon is higher than the band gap of the semiconductor or not. That means it depends on the energy, that means it depends on the frequency or wavelength of the photon. Okay, so alpha is wavelength dependent. And what is the unit of this alpha? We know that this term, so this is number of photon, this is number of photons, so exponential, this term should be unitless, right? So x we normally denote in semiconductor the dimension of length we take as centimeter, right? So the dimension of unit of alpha will be semiconductor inverse, centimeter inverse, sorry. Now we can have a similar expression for intensity of photon also. So I of x intensity is equal to I naught, whatever the initial intensity, exponential minus alpha x. Okay, and this is the intensity if we consider that x point is at the end of this, say, semiconductor. Say this is the length L, and if we are considering the intensity at point x equal to L, if my x equal to 0 is this point and this is x equal to L, then this is the intensity of transmitted power. Okay, transmitted intensity. Okay. Now when we are discussing about optical absorption, we another thing that we discussed, when professor has discussed in the course, is the direct and indirect bandgap semiconductor. Again, all the basic concepts for this week we already have discussed earlier. So this is mainly like application of those concepts for optoelectronic devices. Okay, so another concept that was direct and indirect bandgap semiconductor. So what are direct and indirect bandgap semiconductor? How we can say whether the material is direct bandgap or indirect bandgap? How we determine that? We determine from the EK diagram. If you remember, in the initial part of the course, we discussed about quantum mechanics, how we get the band structure. Okay, so this is the band diagram, which is energy versus x. This is the x, physical dimension of x. What is EK diagram? It is E versus energy versus K, right? EK diagram we call it as a band structure, and what is K? This is the wave number. So this is the inverse of this x. This is like the Fourier transform of x. I mean, I think that you all are from electronics background, so you know what is Fourier transform. Fourier transform of x is like, K is like Fourier transform of x. It is the inverse of physical dimension. Okay, so it has a unit of centimeter inverse. Whatever the unit of length you take, it is the inverse of that. Okay, so whether a semiconductor is direct bandgap or indirect bandgap, we get this from EK diagram. Say we have E in the y-axis, K in the x-axis, and we have these energy bands. Now how this energy bands appear, this we have discussed in the initial part of the course, like how the energy bands form in semiconductors. Okay, say this is our valence band and this is our conduction band. Typically conduction band and valence band have this kind of structure. This is the shape of the valence band typically, and this is the shape of the conduction band typically. How it happens, I don't know exactly, but in all the band structures, this is, for most of the material, the band structure looks like this: the conduction band and valence band. The shape of the conduction band and valence band, especially at the edge of the conduction band and valence band. Okay. Now there are many energy levels above the conduction band also, and many energy levels below the valence band also. Till this level, the electrons are completely filled, and this from this conduction band level, this levels are empty of electrons. So there are no electrons. Remember, this is at, say, 0 Kelvin. Okay. If the temperature is high, there may be some thermal generation of electron and hole pair. There may be some electrons in the conduction band. Now we have another type of material for which EK diagram will look like this. Okay, this is the conduction band and this is the valence band, and now you can see the edge, this edge of the valence band and the edge of the conduction band are not at the same K point. Okay, so these are indirect bandgap semiconductor and these are direct bandgap semiconductors. Okay, and we know that silicon is an indirect bandgap semiconductor, and gallium arsenide, that is a direct bandgap semiconductor. Now why we are discussing this in optoelectronic devices? Because we know that photon, when electrons and hole pairs are generated and when they recombine, so this process is more easier in direct band gap semiconductor, because this process happens with the help of a photon. Okay, electron and hole pair, when photon hits a direct band gap semiconductor, it is getting absorbed and electron will move towards this point. So there is no change in K, there is no change in momentum, only this energy is changing, energy of the electron is changing. There is energy conservation. We know that energy, momentum, these things overall there is this conservation and laws, right? Energy can neither be created nor be destroyed. You already know this. So this change in energy, how the change in energy, this and basically in this process, when the electron and hole pair is generated, electron gets energy, it moves to the conduction band. Now from where it gets energy? It cannot get energy like it. There must be a source, and what is the source? A photon in this case. Okay. Now here there is no change in K, that means there is no change in momentum. Okay, K is related to momentum, remember. And then in this process actually there is a change in energy as well as a change in momentum. There is a change in K. This change in momentum, that is not conserved, that cannot be conserved only using a photon. We need a phonon for that. Okay, so electron moves to a higher energy, maybe there is some defect state here, there is some extra state, and from here to the conduction band edge, this will go, this may be with the help of a phonon. Okay, so there are we need two types of particles for electron and hole pair generation and recombination in case of indirect band gas semiconductor. And in case of direct band gas semiconductor, whatever the photon hits, I mean if it has higher energy than the band gap, then it can be converted to an electron and hole pair. So the optical absorption is more let's say more efficient in case of direct band gas semiconductor compared to indirect band gas semiconductors. Okay. So I will write a brief summary on that. This is for momentum conservation. Okay. And hence it is not very efficient. Okay. So we prefer direct band gas semiconductor for optical applications. We prefer direct band gap semiconductor for optical application, but that does not mean that indirect band gap semiconductors are not at all useful. I mean, we can use those. What is the reason? I mean, even if it is not efficient, you can see here that it needs a phonon for recombination also, not only for electron and hole pair generation. For recombination also there is a need of phonon for momentum conservation. So that process is also not very efficient. So overall we get a higher recombination lifetime. Okay, so that is useful because the electron and hole pair will not be recombined that easily, so we will have a large number of electron and hole pair for longer amount of time. something like that. So people try to use, because we know that even though silicon is indirect bandgap semiconductor, but people are using it for optical applications also in solar cells and okay. Before going to the discussion next, I will just give you this. So I always get confused with intensity, flux, and all those values, because ultimately we will use those, we need those concepts to solve numericals. Okay, so what is intensity? Just it is not right. What is the unit of it? Intensity is watt per centimeter square. Okay, with the defined with centimeter. Okay, power is watt, intensity is watt per centimeter square. So what is intensity? I is equal to number of photons. Okay, this is per centimeter square per second multiplied by energy of the photon. Okay, so number of photons this, and per centimeter square is this. So we know that 1 watt, what is the relation between watt and joule? You should remember this. This relation is used for what is happening? Okay. 1 watt is actually 1 joule per second. That is the relation between power and energy. Okay, 1 watt is equal to 1 joule per second. So this energy we can write either in electron volt or in joule. Okay, then this is joule per second, so that is watt, and watt per centimeter square. So you can see that our dimensions are correct from this expression. Okay, so whether you are given the number of photons per centimeter square or the intensity or the flux, you should remember these dimensions and do the proper conversion as per the need in the numerical. Okay, for numerical problems. Okay, next what was discussed in the course, first the device, optoelectronic device, that is the solar cell. Okay, solar cells give us power. Okay, so this is the solar spectrum. So you can see this unit is watt per meter square per nanometer. Okay, so meter square, watt per meter square, so it is also per nanometer. And from this, this is the standard solar spectrum that people use for, like, to calculate. People design solar cells and they try to calculate different factors, different characteristics based on the solar spectrum, because ultimately it is going to use this spectrum. Okay, but till now whatever we discussed about with respect to number of photons or the intensity. So there are this conversions from this to this photon flux. Okay, how the conversion can be done, that is given in the class. It is not discussed in detail. I also don't work in solar cells, so I have never done the conversion and proper analysis by myself. So basically what is done, so intense irradiance, so this is it has unit watt meter per meter square per micrometer inverse. We can take nanometer, micrometer, whatever. So this can be converted. So this is Fy, that was denoted as it was denoted in the class, and Fy can be converted to photon flux that has a unit meter inverse per meter square per centimeter inverse. So this has unit like this. Okay, can see how we can do the conversion. Like if we are given in the numerical, how we can convert, how we can do the actual analysis of solar cell. So this, and then per lambda, that is in micrometer, can be done. So this is photon flux, means number of photons per centimeter square or per meter square per second. Okay, so that is the unit of flux per meter square or per centimeter square per second. So irradiance, that is calculated, actually it is not calculated, it is like the standard spectrum. The relation is with the photon flux as this. Energy of photon at that particular wavelength and some delta lambda, maybe like 1 micrometer or so. Okay, so this photon flux, this phi is plotted here. You can see this is number of photons per centimeter square per second. Okay, so in calculations we will either use this number of photons or photon flux or intensity. Okay, this is just to show that there is this relation, and people who work in solar cells, they use this spectrum and to find this photon flux. Okay, it's just like that. Another term, how the electron and hole pair is generated. Say if we are considering all the photons heating the semiconductor, that is creating one electron and hole pair. So we are not considering efficiency at this point. So if that happens, so our generation rate for electron and hole pair will be electron and hole pair generation. I am writing this term G dash as per the book Niemann. Okay, there may be a different term, maybe sir has used some different term also. That is alpha intensity x and then h. So this is basically energy. So this intensity is it has a unit, energy per centimeter square per second. Okay, energy per centimeter square per second. Okay, this is the energy per centimeter square per second. Energy, whether you write in joule or electron volt, that's a different meter. Alpha into I of x, that is the rate at which energy is absorbed per unit volume of the semiconductor. Okay, because this, even though the intensity is this much of photon is hitting that much of energy, that has to be again dependent on the absorption coefficient, whether the semiconductor can absorb it or not. Okay, so that is why it is multiplied with alpha, and this amount of energy is absorbed by the material, and if we divide it with the energy of each photon, then this is the energy of each photon. Then we get the generation rate, that is the number of photons that is being generated per unit time. Okay, generation rate means that. Okay, so what is the unit of this generation rate? This is energy per centimeter square per second. So there is this energy again, so energy will get cancelled. What is the unit of alpha? Absorption coefficient, centimeter inverse. So generation rate, the unit will be whatever the number of electron and hole pair that is being generated per centimeter cube per second. Okay, that is the unit of generation rate. Okay. While doing numericals, pay attention to the units, what is given to you, and how we can actually calculate whatever is being asked in the question. Okay, unit of intensity and unit of this generation rate and flux. Okay. Flux is a number. Okay, that is why the unit is this. flux when we multiply it with energy, that gives us the intensity. Okay, number of photons, this you multiply with the energy, that gives you intensity. Okay. Now we already know the basics of everything, how optical absorption happens, and we have studied about p-n junction in this course. I mean, in several weeks we have studied. Now, what is a solar cell? Solar cell is basically a p-n junction, but how we use it, how we normally use the p-n junction, so for rectifying behavior. So normally p-n junction, p-n diode we use for rectification, right? In that case, I mean, whether it's in forward bias, it can allow to flow current, and in reverse bias it does not allow. Okay, we can use the same like a p-n junction as a solar cell. Okay, how we can use it? So we use the p-n junction to generate electricity, right? And how we use it in reverse bias. Okay, so this is basically p-n junction in reverse bias. So this is the p-n junction, this is p side, this is n side. We have this depletion layer, right? So we have an inbuilt, this is the depletion with W, and we have an inbuilt electric field which is in this direction, right, from n side to p side. So this is plus, this is minus. So this is the direction of inbuilt electric field, which is negative. You remember when we discussed about p-n junction, we have an electric field which is like this, right? This is negative. I mean, if I consider my x is in x positive in this direction, then my electric field is in opposite. That's why you get the negative electric field. And we apply this p-n junction as a when we use it in reverse bias. I have not written reverse bias. p-n junction in reverse bias. Okay. Now, if due to photon absorption, some electron and hole pair is generated in this depletion region, what will happen? There is this electric field, and because of this electric field, holes will move towards this direction and electrons will move towards this direction, right? Because of the presence of electric field, there will be a separation of electron and hole, and there will be movement of electrons and holes. Okay, movement of charged particle will give us current, right? So when holes move in this direction, electron move in this direction, so my hole current direction will be like this. This is due to hole, and my electron current direction will be also this, right? This is the electron current direction, because the current direction by convention is opposite to the movement of electron. So overall I will get some current. This is due to light in this direction, the way we have the electric field. So this is basically N to P. You remember in forward bias, when we use p-n junction in forward bias, our current direction is from P to N. In this case, we are getting a reverse current from N to P. And if our number of electron hole pair generation is much higher, compared to whatever the already pre-existing reverse saturation current, then we will have a large photocurrent. Okay, large current due to this electron and hole pair generation. So that is the current we are getting, and from that we can use the solar cell for electricity, right? So whatever our current will be, this is NQ, this is drift current because it is due to the electric field, right? So it's due to drift. So this drift current, we know the expression for drift current density, NQ mu into electric field. Okay, so this N, I mean I'm considering this as say N, there will be P component also. This is proportional to, almost equal to, if we consider that our efficiency is very high, say there is no absorption of these holes and electrons while they are trying to cross this depletion wave. If that is the case, then this N will be proportional to or almost equal to number of photons. Okay, again we are considering that each photon is generating one pair of electron and hole, right? Now in general, what happens if we have forward bias? We have this P, N. P is connected to positive terminal of a battery, okay, VA, and N is connected to negative terminal. So our current direction is this I, diode current direction. Okay, what happens in reverse bias? The P side is connected to negative terminal, N side is connected to positive terminal. This is VA. VA is negative in this case, so this is like minus VA, what we consider as VR, reverse bias voltage. By convention we take this as negative and VR as positive. Okay, so in this case we have a current direction is this. So this is my reverse saturation current from N to P. And what happens in solar cell? We don't use a battery, we just shine light. I mean, that is the light that is around us, I mean, solar light, solar radiation, and because of that there will be this current in this direction. Okay, and if we place a resistor, this resistor can be a light, right? Any load, okay, it can be any load, whatever we are connecting to the solar cell, there will be a flow of current through this load, okay, in this direction. Again the direction is from N to P. Okay, so what is our current expression? I mean, in general I will write the current expression as minus IL plus IS. So this is the photo current, this is due to light, that is why we are using this convention IL, plus the diode current exponential QV by KT minus 1, that is our total current. Okay, this is what happens in solar cell. We have the normal diode current, on top of that we have this current due to photons, and when we are applying, when we are using this in reverse bias, so this current will be negligible, the diode current will be negligible compared to the whole current. So even when we don't apply any reverse bias voltage or we are simply connecting to a load, we get a photo current, and that is how we are generating electricity, right? There are few terms associated with solar cells. So first is the short circuit current. Okay. So this is when V is equal to 0, that means there is no load, R is equal to 0, so that means there is no voltage across this resistor, so V is also equal to 0. In this case, that is the short circuit. So in this case our current will be minus IL is equal to ISC. Okay, there is, it is short circuit means V is equal to 0, exponential, this is 1 minus 1, so this is 0, that is our short circuit current. Okay, and then another term is the open circuit voltage. So VOC, that is when this is open circuit, right? So this will be, if you solve how we can solve it. We know that our current is 0, I is equal to 0, then we can solve it. Then we will get the open circuit voltage as kT by Q ln of 1 plus of IL by IS. Okay, so this kT by Q, what is the another term of is the thermal voltage Vt. Okay, in some numericals maybe this is given as Vt. Okay, then there are other terms associated with solar cell, that is like fill factor. Just give you the formula directly. So this is Vm into Im by Isc by Voc. You know what is Vm by Im? This is the voltage and current for which the solar cell is generating maximum power. Okay, so I think you already remember the IV characteristics of solar cell. For normal diode, it is like exponential in forward bias and very less current in reverse bias, right? What happens in solar cells? We have a slightly higher current. We have like this. Okay, so this is my open circuit voltage, this is my short circuit current, and for this some point here for which we get this maximum power. What is power? I into V, right? That is the maximum power delivered to this load. And how we can calculate it? Maximum power dP by dV, say that will be 0. Okay, this is how we find the maximum point, right? Normally, so we use this and we find this. It cannot be calculated directly. It is not easier to calculate directly. That is why people are like often try to find this ISC and VSC, because these are easy to calculate, easy to measure. Okay, open circuit and short circuit. Okay. Now fill factor for most solar cells are in the range 0.7 to 0.8 around. Again, I have not worked in solar cells. Whatever I am saying, that is based on this book, and sir is also following this book in the course. So this is Neiman. If you are more interested, you can study this book to clarify your concepts. Okay. So this is briefly about solar cells, and then what other optoelectronic devices that was discussed, that are photodetectors, right? What are photodetectors? As the name suggests, it detects photon, right? And how we can detect photon? First device was photoconductive detectors. How it is implemented? The conductivity of semiconductor, that is changes when we shine light. Okay, that is due to electron and hole pair generation in the semiconductor. Okay, so because of that, the total current that is flowing through a semiconductor, initially say it was J0, that will change to J0 plus JL. So this is due to change in conductivity after shining light. So how it changes? So initially, so this J, we are considering the drift current density. So we have a block of semiconductor, we are applying some voltage, that means we are applying electric field across this voltage, and because of that electric field there is movement of carriers. Okay, so this J0 is it is equal to whatever the conductivity initially and whatever the changes happen, the change in conductivity that is happen multiplied by electric field. This is the Ohm's law, right? J equal to sigma into E. Now this delta sigma, that is equal to Q into delta N into mu N. This is the general expression of conductivity. Q into delta P into mu P. Now we know that electron and holes are generated in pairs, right? When photon hits, one electron is generated, one hole is generated. So that means our number of excess electrons and number of excess holes are same. So I can write this as Q into delta P or delta N, whatever you use, mu 1 plus mu 2. Okay. These are the excess carriers. So what is the unit of this delta P? This is number of holes or number of electrons per centimeter cube, right? So how many number of excess carriers are being generated due to the shining of light? This is equal to whatever the generation rate. Remember we discussed about generation rate, right? Photon is incident, how the generation rate we can calculate from the intensity of photon and the absorption coefficient, right? That generation rate multiplied by tau P. So this is the generation rate. This is recombination time. Okay. These many photons are this many electron and hole pairs are generated and per unit time, and we have to multiply with recombination time because after that time that will be recombined. Okay, so see, we know that this has a unit number per centimeter cube, right? Generation rate, what is the unit? Number per centimeter cube per second. So always check the dimensions whether we are doing it correctly or not, per second, and it has a unit second, right? So yeah, dimensions are correct. We are getting the excess number of carriers. These are generated due to absorption of photon, optical absorption. Now this is one way to detect number of detect photons. Okay, now what kind of photon we can generate? The photons, those get absorbed, right? And whether the photon will get absorbed in a semiconductor or not, how it how we can say it, it is based on the band gap of the semiconductor, right? If you want to detect a photon that has it's a very high energy, so band gap will also be such that it can be it is absorbed by the material. Okay, so we can detect the type of photon that is based on the band gap of the semiconductor. That is why we need different semiconducting material to detect different types of photons. Okay, here the problem is that many times we don't get a very large change in conductivity, so we don't get a very large change in the current. Okay, so what people use another type of photodetector, which is voltaic photodetectors, right? Again, these are nothing but PN junctions. Again, these are PN junction when used in reverse bias. Okay, why we use it in reverse bias? We know that when we use PN junctions in forward bias current is already high. On top of it, that if some minority carriers are generated, some excess carriers are generated due to shining of light, then that may not be detectable, that delta I may not be detectable. But in reverse bias, in PN junction the reverse saturation current is very low. If somehow we can absorb enough photon and generate enough electron and hole pair, we'll get enough current that can be detectable. Okay, so that is why we use it in reverse bias. Okay, so when there is no light, so J dark, current density in dark when there is no light, this is approximately equal to Js, which is the reverse saturation current. And when there is light, we have this expression, how the derivations are given, how water the assumption, those were not discussed. So this is Ln plus Lp into Zl. So this is the photo generated current. W is the depletion width. If we have a larger depletion width, we can have more number of electron and hole pair generation, and that basically increases the current. L and N, LP, these are minority carrier diffusion length. You already know that there should not be any recombination. Okay, holes should go towards the p side and electrons should go towards the n side in the neutral region. There should not be any diffusion in between, so it depends on the diffusion length. If the diffusion length is more, it can diffuse to a longer length, then we get more current. So that is why this is again directly proportional, and of course it is directly proportional to the generation rate. Okay. So this JL will be on top of this reverse saturation current, and this should be significantly large. The photo current should be significantly large than the reverse saturation current. Then only we can say that is a good photovoltaic detector. Okay, if you design a photovoltaic detector, say for detection of particular wavelength of photon, for which you are getting a very low JL even for a large number of photons, then this is not a very good detector. Okay, maybe we have to change the material so that the absorption coefficient is high, the efficiency is high. Okay, we have to select the right material for the right kind of detectors. What is the problem with this PN junction as a photodetector? Again, the depletion width is limited, so current is also limited. So what people moved to like the next device that comes after this, the next type of photodetector, that is the PIN diode, for which we have a larger depletion width. Okay, we have a larger depletion width. We have this P side, normally it is P plus. Remember I told you earlier that it is easier to make a P plus device and then to make a contact that will be ohmic, rather than if we directly try to do make a contact that may not be ohmic, that may be rectifying, right? We have studied about different types of metal semiconductor contacts earlier. Some contacts may be rectifying, some contacts may be ohmic, right, based on the work function of the metal and semiconductor. Whereas if we make a P plus or N plus region, that it is easier to make a contact with that, and they almost behave like a metal. Okay, so there is no you don't have to worry about whether the contact is metallic or ohmic or rectifying. Okay, we have P plus region in PIN diode. This is the intrinsic region, and then we have the N plus region. Okay, this P plus region is normally very thin, so that when we shine light from this side, whatever is generated, those will move towards the depletion region. Okay, the whole intrinsic region is the depletion region in this PIN diode case. Okay. So how we have the electric field? This is again similar to the PN junction. We have the electric field in this direction. Okay, we have studied about how we can find the diagram is. So we have this P plus So if this is my charge density, so this is my minus q Na from p plus side, and this is my plus q, that is q into Nb, right? So my depletion width is this whole width, and my electric field is like this, right? We have a larger depletion width, and our electric field is again negative. So in this direction, x is positive, in this direction I am taking, so electric field is in this direction, it is negative. When electrons and hole pairs will be generated, again holes will move towards this direction, electrons will move towards this direction. So overall I will get a current due to light, due to photons in this direction. Okay, similar to the p-n junction, the difference is that we have a larger depletion width now. Okay, so basically we have large area for creation of electron and hole pair. Again, how we can derive the current expression in PIN diode, that was discussed in the class. And write down the expression. So that is Q phi naught 1 minus exponential minus alpha into W. Okay. So this is phi naught, this is the photon flux, and we are considering that our generation of electron and hole pair, I mean intensity of our light is high, or the number of electron and hole pair is high, and it decreases. Our photon flux actually decreases like this. So that is why we have this 1 minus exponential minus alpha W, this term. So this W is the width of the depletion layer. Okay. There are certain assumptions while finding this expression. We are considering that there is no recombination of electron and hole pair in this depletion width region. Yeah. Another type of device, the next one is avalanche photodiode. We have already studied about what is avalanche multiplication and avalanche breakdown. This basically, like one electron and hole pair will create another, like, so electron will hit, it will create electrons, so it will create 2 more electrons. Okay, basically there is this multiplication. Okay, and how it happens, we create like a large electric field region. When the electric field is large, so electrons and hole will move faster. Okay, that will hit and create another, it will have enough energy to create another electron and hole pair, and that will create another electron and hole pair. Okay, that is the basic mechanism. We have a multiplication factor m. Okay, for each photon we actually will have, instead of 1 electron and hole pair, we will have m electron and hole pair if m is our multiplication factor. This happens when we have a device structure like this, n plus p, p minus, p plus. Okay, and in between this region, n plus p region, we will have a large electric field, and that large electric field actually create this avalanche effect. Okay, because of large electric field, electrons will get high energy, that will do this multiplication. Okay, it will create more and more number of electrons. That is why we try to avoid very high electric field in our devices. That may lead to breakdown of our device. Okay? If the electric field is very high, it can create more and more number of electrons. If the temperature is very high, so remember we have studied about this breakdown. Okay, how our device breakdowns in case of p-n junction. There will be large number of currents, there will be large number of electrons and holes. Okay, but in this case, the device configuration is designed in such a way that it is actually helpful for us. For one photon, we are actually getting m number of electron and hole pair, and that's how our photocurrent is much higher. Okay? I hope that there is no doubt. I will go to the questions next. So the first question is, two beams of light with same initial intensity pass through two different materials with absorption coefficient so alpha 1 is 10 to the power 2 centimeter inverse and alpha 2 is 10 to the power 4 centimeter inverse. After passing through a distance x equal to 1 micrometer, 1 centimeter. Which of the following statement is true? So what is the answer? So we know this expression, right? I at any point is equal to I naught exponential. There is an exponential decay of intensity of the photon due to absorption in the material. Now absorption depends on absorption coefficient, so the expression is I naught minus alpha into x, right? X is the distance at any point. So this is known as, this law is known as Beer-Lambert law. Maybe you have studied this somewhere in physics. So from this law we can say that higher the alpha, lower will be the intensity. So my alpha 1 is 10 to the power 2, alpha 2 is 10 to the power 4. That means my I1 of x, because x is same, I1 of x is actually greater than, because alpha 1 is lower than I2. So the answer is B. Now, when this will happen? When alpha is same, right? Basically the same material. This is not possible. This is only possible when alpha 1 is higher than alpha 2. Can this be possible? Both intensities remains unchanged. This may be possible if our absorption coefficient is very low, right? If it is, when cannot be ideally 0, but if it is almost 0, then I of x will be I naught, right? So that means even at the end of the semiconductor, end of the material, my intensity will be same. That means for that light, my material will be transparent, right? If you are given like to find out the intensity for a particular wavelength, for a particular material, then so you can do the calculation based on the given alpha and x. You can find out the intensity and just pause and think for like 5 seconds whether the value is correct or not. I mean, you know that for visible light, for silicon, if x is large, then the intensity should be very low, right? Silicon is not transparent. If it is a transparent material for visible light, the intensity should be almost equal to I naught, right? So that's the question. Consider gallium arsenide at T equal to 300 Kelvin assume the photon intensity at a particular point be very careful with what is given to you. This is intensity, okay? At a point is I nu of x. I mean, this is again intensity is frequency dependent, like it depends on the photon, right? It is equal to 0.05 watt per centimeter square at a wavelength of 0.793 micrometer. The typical absorption coefficient of sunlight is 10 to the power 4 centimeter inverse, say around this wavelength. What is the steady state? Excess, what steady state means, it is not time dependent, okay? If we are shining light, then we are shining light continuously, then it's not changing with time. Steady state excess carrier concentration we have to find it in per centimeter cube, that is the carrier concentration, unit of carrier concentration. If excess minority carrier lifetime is 10 to the power minus 7 second. Okay, this is steady state where shining light continuously of this wavelength, but then again the electron and hole pairs are generated, but those generated electron and hole pairs will have certain lifetime. Okay, after that time it will recombine. So that is why this information is also given to us. So we have to find the excess carriers concentration. Okay, let's find this. So I is given to us, that is 0.05 watt per centimeter square. So we know this I is like number of photons per centimeter square per second. Okay, and we multiply with energy of each photon. This we have already discussed. This is intensity. What is flux? Flux is, so this is my flux actually, 5. So my photon flux is flux will be 0.05 watt. I have told you earlier watt is equal to joule per second, right? So I'll write it that joule per centimeter inverse. You don't have, I mean you can very easily calculate it directly. I'm just writing each and every step. Okay, so that there is no mistake. And then I have this centimeter to the power minus 2. This multiplied by not multiplied, divide by E of h nu, energy of the photon. This also I have to calculate in joule. Okay, so that there is no mistake. Yeah, then I will get flux. So this will be 0.05 E h nu. We know that this is 1.24 divided by lambda in micrometer, right? So my lambda in micrometer is 0.793, but this actually, so energy is equal to 1.24, energy is equal to actually hc by lambda, right? So hc, if you multiply this and if you write lambda in micrometer, okay, then we have this expression 1.24 by lambda in micrometer. This gives us energy in electron volt. So this is my energy in electron volt. I have to multiply with Q, 1.6 into 10 to the power minus 19, so that I get the final answer in joule, energy in joule, so that I get the correct result. Okay, so this you can calculate. This will give me roughly 2 into, I have already calculated, so but check the calculation from your side. This will be centimeter to the power minus 2 second inverse. Right? Yeah, if you don't multiply this, you will get some number that will not be correct. And how we can see, flux is like, this is the number of photons that are hitting per centimeter square per unit time. So that has to be a, I mean typically it should be a large number, right? We don't hit 1 or 2 photon, that will not do much change. So this is a 10 to the power 17. This is like a reasonable number for photon flux. Then I can calculate my generation rate. Okay, now I know the flux, I can calculate generation rate. GL I am writing, this is alpha into phi. This equations I have already discussed earlier, I am using it. Okay, so this is my centimeter square second, so I multiply with alpha, so I will get number of electron and hole pair that is generated per unit time, right? So this will be alpha is given to me as 10 to the power 4 into 2 into 10 to the power 17. So this is 2 into 10 to the power 21 per centimeter cube per second. So this is my generation rate of electron and hole pair. So what is the excess carrier? Excess carrier concentration, delta P or delta N will be whatever the generation rate, that is multiplied by lifetime. Okay, for this time, I mean the carriers are present. Okay, so this will be 2 into 10 to the power 21 into tau is 10 to the power minus 7. So my final answer is 2 into 10 to the power 14. This will be per centimeter cube. Okay. So this is my final answer, 2 into 10 to the power 14. I hope this calculation is clear. This is how we can get if the intensity is given. If the flux is given, you don't have to do this calculation. You can use the flux directly to get the generation rate. If the generation rate is given, you can directly calculate the excess carrier concentration with the help of minority carrier lifetime. Okay. Next question. A single solar cell with maximum solar efficiency of 12.5% produces a voltage 1 volt and maximum current 2 ampere. The solar insolation is 1000 watt per meter square. This is the incident intensity. What could be the area of solar cell in centimeters square? Options 360, 1600. Okay, so efficiency of solar cell, this formula I have not discussed today, but you already know that was discussed in the lecture videos. This is whatever the output power that we are getting and the input power. Output power is our voltage into current. Okay, normally we find it at the maximum power point, Vm into Im. And input power is whatever the photon is incident, whatever the photon energy or the light energy, light power. Okay. So my P in will be, efficiency is given to us, so Vm by eta. So this is the maximum point and it is given, so Vm is 1 volt and my Im is 2. Efficiency is, so 12.5% means 0.125. So this is, what is the value? 2 by 0.125. 16. And the unit is watt, right? This is the power. Vm into Im. So voltage into current. So this is watt. How we can find area? Total power insolation is this, like watt per meter square. This is given. This is the intensity of the energy. Okay. So power area, how we'll calculate? This is whatever the input and this P. So this insolation. Okay. Whatever the intensity. So this is my 16 and 1000 per meter square. So that will be, I have to write it in centimeter square, right? So into 10 to the power minus 4. So this is 10 to the power 3, this is 10 to the power minus 4, so this is 160 per centimeter square. I mean not per centimeter square, this is already per centimeter. So this is 160 centimeter square. So this is the area of the solar cell. Okay, so my final answer is C. Yeah, I hope it is clear, and if you have similar questions in the assignments, then you will be able to solve like this. There are many concepts of this in solar cells and in photodetectors. So I have skipped a few. Let's solve few questions, then it will be easier to understand. A photodiode has a responsivity of 0.5 here per watt at 850 nanometer. Find the efficiency of the detector. In case of photodetectors, we have this term responsivity. This responsivity, how responsive our diode is to photon, right? So basically, responsivity denoted with R, that is equal to, I don't remember the formula, so I have written it down. This is eta efficiency divided by this energy of the photon. This is in electron volt. For that particular photon, how much it is responsive. This eta is efficiency of the photodiode. And how we calculate eta? Eta is known as the quantum efficiency. Okay. So this eta is, for say I have some current I, that is equal to eta q into P by h nu. Okay. So P is the electron and holes which are in pair, excess carrier basically. So basically the current is whatever the efficiency into multiplied by photon flux. Okay, and Q of course, because we have to multiply with the charge. Whatever the flux we multiply with, so ideally we want efficiency to be 1. Okay, so what our current we want, all the photons, Q will come, the charge, all the photons that are coming, that is creating our the flux. Okay, whatever the photon flux, and that is multiplied by Q. Ideally we want this current. Okay, all the photons are responsible for the photocurrent. We don't get that, we have some less current, that is our quantum efficiency of the device. Okay, we expect some current due to some photon flux, but we get some current. Okay, the difference, this is based on the efficiency of the diode. And this eta responsivity, how we calculate, using this formula. So these are formula, please remember these formulas. Okay, now our responsivity is given at a particular wavelength, so we can calculate energy and we can find out the efficiency. So our eta will be R into energy. Energy we know that this is h nu, so this is 1.24 by lambda in micrometer, right? So this is 0.5 into 1.24 by 0.85. This will be this is 0.73, so that means it is 73%. Eta is 73%. This is my answer. Consider a silicon PN junction at T equal to 300 Kelvin. Na is given to us as 5 into 10 to the power 18 per centimeter cube. Nd is given to us 1 into 10 to the power 16 per centimeter cube. The N, so diffusion coefficient is given 25 centimeter square per second. dP is given, whole diffusion coefficient 10 centimeter square per second. Tau N naught, minority carrier lifetime for electron, 5 into 10 to the power minus 7 second. Tau P naught is 1 into 10 to the power minus 7 second. Let the photocurrent, that is IL, current due to photon, the density JL equal to IL by A. This is equal to 15 milliampere per centimeter square. Okay. Calculate the silicon PN junction solar cells open circuit voltage. What is the open circuit voltage formula? Remember this, right? We say this I total is 0, so if we arrange this expression, we get the open circuit voltage is this. So VOC, open circuit voltage, is KT by Q ln of 1 plus IL by IS. So current, we can write it in terms of current density, so that area term will get cancelled out. So this will be KT by Q ln of 1 plus of JL by JS, right? JL is given to us. We have to calculate GS, which is the reverse saturation current for PN junction. Okay. So JS, what is the expression for JS? You must have remembered from lectures of PN junction. So this is Q dN by Ln into NP naught. Okay, for electron drift, and then dP, electron diffusion, dP by Lp into Pn naught in the n side. Okay, so what is Np naught? This is the equilibrium electron density in the p side of PN junction. This is the hole density in the n side of the PN junction. Okay, so this Np naught, this is in the p side, so Np naught is, how we can find this, I square Ni square by Na, right, from mass action law. This Pn naught, by this term you all, this is week 11, so you already know this expression. You should, even if you remember, even if you don't remember, you should know that this I'm writing this naught, that means this is equilibrium. So in equilibrium, we can use mass action law. So N into P is equal to Ni square, intrinsic carrier density. So Np will be Ni square by P. So P in P side of PN junction is Na, right, except doping concentration. So this is also similarly Ni square by Nd. So my expression is Q into Ni square dN by Ln into Na plus dP by Lp into Nd. dN and dP are given to us. Ln and Lp we don't know, but we know this expression, right? Minority carrier diffusion length for electron, this is equal to tau n into dN. So this tau n is given to us 5 into 10 to the power minus 7. dN is 25. So I will write it in terms of centimeter. Okay. this is 3.5, 3. If I make calculation mistake, then let me know, minus 3 centimeter. Okay. Similarly, LP will be tau P into dP. So this is 10 to the power minus 7 into 10. So this is 10 to the power minus 6. So this is 10 to the power minus 3 centimeter. Ni, this is silicon, so I will roughly take, this is at 300 Kelvin, so Ni I will take 10 to the power 10. Okay, you can take 1.5 into 10 to the power 10 also, but in the question it is not given. So this is 1.6 into 10 to the power minus 19. I will take Ni as 10 to the power 10, so Ni square is 10 to the power 20. 25. Write everything in centimeter. 53 into 10 to the power minus 3. And A is 5 into 10 to the power 18. Plus 10 by 60. We'll get some JS. Okay. This is what will do. If we do it 10 by 10 to the power 13, so 10 into 10 to the power minus 12. This will be roughly 1.6 into 10 to the power minus 11. This is ampere per centimeter square. Right. So my VOC will be KT by Q is 300 Kelvin, so that will be 25 millivolt, right? I am calculating voltage, so 20.025 ln of 1 plus IR by JS. This is roughly 0.51 volt. Please check the calculation if I have made any mistake, but the process is this. Next question. consider two silicon PIN diode. Here we have the photon flux, not intensity. So we know the expression for PIN diode. So the current density expression was JL Q into phi naught 1 minus exponential minus alpha into W. So that means my Q is a constant, phi naught is same for both the diodes. So my JL is basically proportional to 1 minus exponential minus alpha into W. So JA by JB will be 1 minus exponential minus alpha A into W, 1 minus exponential minus alpha B into W. Okay. So this is 1 minus exponential minus alpha is 10 to the power 3 and my W is 20 micron. So in centimeter this is 20 into 10 to the power minus 4 centimeter, right? So then 20 into 10 to the power minus 4 into 10 to the power 3, this will be 2, exponential minus 2, and this is 1 minus exponential, this is 10 to the power 2. So if I multiply with W, then this will be 0.2, minus 0.2, right? So this value will be 1 minus exponential minus 2 divided by minus exponential minus 4.7. Don't have to calculate the whole current, just ratio wise asked. Right? this question was asked in GATE 2024. Okay, so the photocurrent of a PN junction diode solar cell is 1 milliampere. The voltage corresponding to maximum power point is 0.3 volt if the thermal voltage Vt is 30 millivolt the reverse saturation current of the diode the reverse saturation current was asked. I don't know why the expression is given as ISC to calculate reverse saturation current in nanoampere. What is the value? So that's okay. So I have to find out. So it's a solar cell, and what is given to us? Vt is given to us 30 millivolt. And photocurrent IL is given to us 1 milliampere. Okay, and this is corresponding to its voltage 0.3 volt. Okay, this is the maximum power point. So I have to find out IL. So let's consider the total current of this. So you have this expression IL, whatever the photocurrent, that will be in the reverse direction with respect to the normal diode current, right? So this is IS exponential QV by KT, right? This expression I'm asking. So this is QV by KT, and KT by Q is our thermal voltage, right? So I'll directly write that in the expression. So this is my voltage by Vt minus 1. Let's take for the calculation, this is as positive and this is as negative. Okay, this is the convention. We are considering whatever the photocurrent, that is our positive direction of current. Okay. So what is the maximum power point? This is the point where dP by dV is 0. Remember, that's how we calculate the maximum power point. Derivative is 0 at this point. So this power is dV into I by dV equal to 0. So this I plus V, doing partial derivation. So dI by dV is 0. and my what is my I by dV? So this is my total current, right? So this is minus IS. This is my photocurrent is my constant, that is with respect to V. So this is 1 by Vt, thermal voltage exponential V by Vt, right? This, okay, so this is my derivation. So in this expression it will be I minus V Is 1 by Vt exponential V by Vt. So this will be exponential. This is my I. Again my I is actually this, so you can write it here, IL minus IS exponential V by Vt minus 1. This is equal to V by Vt at maximum power point Is exponential V by Vt. So I can rearrange the terms. IL is equal to Is exponential V by Vt minus 1 plus V by Vt exponential V by Vt. Okay. So this is equal to Is. I mean, there may be a direct expression for this, but this is the way how we can do the derivation. Actually, I solve it like this. So exponential V by Vt 1 plus V by Vt minus Is. So this term is this. Now I can write that my Is is I can neglect this term because the reverse saturation current is actually much less compared to the photocurrent, right? So I can write that my IL is approximately equal to this term. So overall, right from here I am going here. Okay. So I can write an expression for Is, because I have to find the reverse saturation current, that will be most equal to IL by exponential V by Vt 1 plus of V by Vt. Okay. Yeah, if you don't do this derivations also, maybe there is like this expression is actually known, but how we can get this through this process. Okay. We have to find the derivative of, because we are considering maximum power point, so dP by dV is equal to 0, and from that we actually get this expression. Now we can calculate, right? We have the values, we know IL, we know V, this is 0.3, and Vt is 30 millivolt, so I can calculate everything. So this is 10 to the power minus 3, because this is 1 milliampere, and exponential 0.3 by Vt is 30 millivolts, so this is 0.03, 1 plus of 0.3 by 0.03. You can do this calculation, and finally we get the expression as 1.127 nanoampere. Check the calculation again. I think this is correct. Okay. So this is my final answer. Still one more question. So this graph is given. So this is for a this has, so let me write down the question. So the diagram identify minority carrier concentration and photocurrents in a reversed bias PN junction. So we know that in PN junction, in reverse bias, the minority carrier concentrations looks like this. When we consider depletion approximation, this is my X. This is my, say this is P side, this is, okay, so that in the diagram this is N side, this is P side, this is, say, my edge of the depletion region in P side, XP, and this is my minus XN of the depletion region in N side. So the minority carrier concentration in the bulk or in the quasi-neutral region away from the junction is in the N side, this is P N naught, whatever the equilibrium concentration. So this is Ni square by Nd, right? And it goes to 0 here because of the electric field. And this is like this. Okay. This is equilibrium hole concentration in the P side. Equilibrium electron concentration in the P side. So this is Np naught, which is equal to Ni square by Na, right? So we have an electric field which is in the direction, in which direction we have PN junction, right, like this. So we have the depletion region here, ionized acceptors in P side, ionized donor in this side. So we have an electric field from N to P. So electric field is in this direction, right? Okay, so among these four, either A or C is our correct option. Now with photo generation, there will be electron and hole pair, and holes will, because of the electric field, holes will go towards this side. So the hole concentration will increase here. So it's like this, and my hole concentration, electron concentration increases because electrons will move in this direction because of the electric field. Okay. So these are my excess carriers. Okay, So these are excess scalars. These are excess scalars. Now my holes are moving in this direction because of the electric field. So my hole current is in this direction, right? Electrons are moving in this direction, so by convention my electron current is also in this direction. So this is my Gn. So my overall current is in this direction, N to P. Okay. So what is the correct answer from this two diagram, A or C? So correct answer is A, right? We have the currents in from N to P. It's not from P to N. Solar cell in reverse bias in PN junction, and especially in solar cell when we have excess scalars, we have a large current in the reverse direction. By convention, like in PN junction and forward bias, we have current from P to N. Okay, so my answer is A. So we already have, it's already 8 p.m. If you have any quick doubt, you can ask. Otherwise, I will stop the session. Okay, so if there is no doubt, then let's stop the session here. Let's meet in the next week, next Tuesday, or maybe I will have one extra session on Friday. Okay, this you will be notified when we will have the session. Thank you for attending the session. I hope it was useful.